Welcome all of you. In the previous class we discussed the topic geometric progression, its concept and also the formula related to nth term as well as the sum of n terms. And we also discussed some of the problems based on the geometric progression. Today I am going to teach you some important problem based on the 9.3 exercise related to GP. So we are going to see the first question. Please see the question. This is question number 18 of 9.3. Question is, find the sum of this 8 plus 8, 88, 888 up to n terms. So we have to find the sum of a particular series given up to n terms. Now, as the sum is set in this question, what we have done, 8 plus 88 plus 888 plus 8888 up to n terms, we have to add that. Now this is written as like this, taking 8 common. This is a format question, we have to follow the format very carefully. Take 8 common. What we have, 1, then 11, then 111, then 1111 up to n terms. Now whenever you see this type of question containing the same number of terms, same digits, so in that what we need to do, we need to multiply and divide the numerator and the whole term, the denominator and the whole term by 9. So what we get, 9, 9, 99, 999 and so on. What we have done, we have divided by 9 and multiply the whole expression by 9. Now this 9 can be written as 10 minus 1. This is 10 square minus 1. This is 10 cube minus 1 up to n terms. Now after this we get a series 10 plus 10 square plus 10 cube up to n terms. And minus 1 is repeated up to n terms. So minus 1 is going to multiply with n. We have minus 1 into n, which is minus n. Now this forms a GP where first term is 10 and the common ratio, GP is a sequence having a common ratio. So in this the first term is 10, the common ratio is 10. So we apply the formula of sum, which is Sn is equal to a r to the power n minus 1 upon r minus 1 when r is greater than 1. So r is 10, so we have applied this formula of sum. This is a, this is r to the power n minus 1 upon r minus 1 minus of n. Now simplifying this, we get sum is 8 upon 9 multiply by 10 upon 9 into 10 to the power n minus 1 minus n. So this is the required answer of question number 18. Now we will see question number 24. The question is saying that show that the sum of first n terms of a GP to the sum of next n terms up to 2n of the same GP having the ratio 1 upon r to the power n. Please see question number 24 of your NCERT book 9.3 exercise. In this question, the sum of first n terms of a GP I have denoted as Sn. The formula we all know is a into r to the power n minus 1 upon r minus 1. Now this is the GP a1, a2, a3 up to an, and the next term is an plus 1, then the terms goes up to 2n. So then the total number of terms we have 200. Suppose the sum of first 100 terms and the sum of next 100 terms, they should have the ratio we have to calculate in this question. So what we have done, we have taken the terms from a1 to a2n, where a1 to an is the first. We are going to take the sum, and then from an plus 1 to a2n we are going to take the sum for the second case. So in the second case, Sn plus 1 to 2n, we have to find out the sum. I have taken it as Sp, sum of terms from n plus 1 to 2n terms. Now in this case, in the first case the first term is a, in this case the first term is an plus 1. So we all know the general formula of nth term of a GP, ar to the power n minus 1. So I have written sum is equal to a to the power n plus 1, which is not this, this is an plus 1, this is the term an plus 1. Now this an plus 1 is written as a r to the power n plus 1 minus 1. This is as it is because the common ratio is same for the whole expression. Now this can be written as ar to the power n upon rn minus 1 upon r minus 1. Dividing both, all the things eliminated, a and a also eliminated, we get only 1 upon r to the power n. So basically in this question we have to find the ratio of the sum of first 100 terms and then the sum of next 100 terms. So in this we have number of terms up to 2n. We have to find the ratio of sum of first n terms and the sum of next n terms. So in that case we have applied the concept of sum. In first case the first term is a, in the second case the first term is an plus 1. Please see the solution of this question carefully. Now we will see question number 25 of 9.3. The question is, if A, B, C, D are in GP, we have to prove this LHS is equal to the RHS. Now since they are in the GP, the first term is A. I have chosen capital A to help you out with the symbols. Otherwise you will be confused with small a both the sides. This is capital A first term. Second is AR. Third is AR square and the fourth is AR cube. As we all know, the general term of the GP is AR n minus 1. Now the LHS part is A square plus B square plus C square is going to multiply by B square plus C square plus D square. We are just going to put the value of these terms here. So A is capital A square, B is AR whole square means A square R square, C is AR square, so the square of it is A square R4. Again B is AR, so square is A square R square. C is AR square, so the square is A square R to the power 4. D is AR cube, so the square is A square R to the power 6. Now what is common here is A square. What we have inside 1 plus R square plus R to the power 4. What is common here is A square R square. What is common here is 1 R square plus R4. Now these two terms are multiplied and give us A to the power 4 R square into the whole value is same, so they are going to be the square in terms. Now RHS is AB plus BC plus CD whole square. Substituting the value of A, B, C and D here, we get A multiplied by AR, AR multiplied by AR square multiplied by AR cube. This gives A square R, this gives A square R cube, this gives A square R5. Now taking A square R as common, we have 1 plus R square plus R4 whole square. Now taking this value outside the bracket, we have A to the power 4 R square into the whole square of this. So now LHS RHS are equal. So whenever we have 4 terms in JP, these two conditions are going to be satisfied. Now in this question number 28 of your NCERT book, 9.3 exercise, question is, sum of two numbers is 6 times the GP. Sum of two numbers is given as 6 times the geometric mean, not GP, geometric mean. So we have two numbers A and B. The sum of that is equal to 6 times the geometric mean, which is A plus B is equal to 6 times of root AB. Since the geometric mean is the square root of the product of two numbers. Now this can be written as A plus B whole square equal to 36AB. Now we know the value of A plus B. If we can calculate the value of A minus B, we have two equations, and after solving them we can get the value of A and B. So what I have done, I have written a formula of polynomials, of identities related to the polynomial topic. A plus B whole square minus of 4AB gives A minus B whole square. You should try verifying this, either it is correct or not, and then you can easily understand how I have written this. Now the value of A plus B whole square is 36AB. This is minus 4AB is equal to A minus B whole square. This gives us 32AB is equal to A minus B whole square. Shifting the square to the left side, we get plus and minus under root 32AB. This 32 can be breakable, splittable, so it is 4 root 2 AB. Now 4 is outside the bracket and root 2AB is inside the square root. This is A minus B. Now we have two equations. This is first A plus B and this is second A minus B. Now taking only the positive terms here, we can take the negative also. I am taking only the positive one. So the two equations are A plus B as 6 root AB, A minus B as 4 root 2 AB. B and B cancel each other. This is 2A. Root AB is common in both and we have 6 plus 4 root 2. 2 divides 6 by 3. 2 divides this by 2 root 2. So the value of A I got is 3 plus 2 root 2 multiplied by root AB. Now substituting this value, or we can also do elimination method to calculate the value of B. By subtracting a, we can get b as 3 minus 2 root 2 multiply root ab. So in these type of question, if you see the value of a comes in positive terms, the value of b should have a conjugate of that. So if it is plus there, it should be minus there. Now taking the ratio of these terms, these two root ab eliminated, and we get 3 plus 2 root 2 ratio 3 minus 2 root 2. This is a very important question, and you need to understand this identity in order to solve two equations and in order to get the equation. Now this is question number 23 of 9.3. In this question, first term of a GP is A, nth term is given as B, which is also A r to the power n minus 1, and P is the product of n terms, that is A multiply AR square multiply AR cube multiply by up to AR n minus 1. Now A is coming in all the terms, so we have A to the power n because it is going up to n terms. And now R has the power of 1 plus 2 plus 3. Since when the base are equal, the powers must be added. So this is 1 plus 2 plus 3 up to n minus 1. Now applying the concept of AP arithmetic progression here and calculating the sum, we get A to the power n into R to the power n into n minus 1 upon 2. You can easily calculate this using the concept of arithmetic progression. Now we have to apply the concept, we have to prove this P square equal to AB to the power n. So what I have done the square of this. So the square of whole terms, this will give us a to the power 2n, and this 2 and 2 eliminated, so r to the power n into n minus 1. Now I am shifting a to the power n to the right side, to the side with r. I have done a to the power n multiplied by a to the power n with this r function. So this r function, this component can be written as a r n minus 1 whole to the power n, like this. Now this a r n minus 1 is what? B. So we have a to the power n multiply b to the power n. Combining, we get ab to the power n. Now I hope all of you understand the problems related to 9.3 using the concept of GP in both the cases, with the nth term also and with the sum of n terms. Now we are going to discuss some of the special cases related to the concept sequence and series. I will let you know some of the special formula related to the sum of special series as well as for the sum of infinite series. So please have a watch on it, look very carefully. Sum to n terms of special series. If we have a sum of first n natural number, which is 1 plus 2 plus 3 up to n, that we can do directly without doing any calculation. We can directly write it n into n plus 1 upon 2. This formula can be used as the sum of first n natural number. Now if these natural number possess a square on it, which is 1 square plus 2 square plus 3 square up to n square, the sum of squares of first n natural number will be n multiplied by n plus 1 multiplied by 2n plus 1 upon 6. So this will be for the first n natural numbers. This will be for the first square, sum of the square of first n natural number, and the next will be the sum of cubes. So 1 cube plus 2 cube plus 3 cube up to n cube, we have n into n plus 1 upon 2 whole square. So whenever you see this type of expression, you directly put sum as this value, for this value, and for this particular value. And now if you get a term of GP having infinite terms, if you get a sequence of GP having infinite of terms, so for that sum of infinite series of a GP, we have a formula a upon 1 minus r, where a is the first term and r is the common ratio. So you have to just go through all these formulas and make a note of it, because it will help you in solving some of the problems. Now I will help you out by showing some example in which you have to put these formulas to calculate the problem solution. Please see it very carefully. Now we will see some of the examples based on the sum of n terms of special series. This is 9.4 exercise, question number 1. Please see, the question is find the sum of this particular sequence up to n terms. This is 1 into 2 plus 2 into 3 plus 3 into 4 plus up to n terms. So what we need to do, we have to first make a general term for the given series, and then we apply the concept of sum formula. Now this is 1 and this is 2. This is 2 and this is 3. This is 3 and this is 4. So each term is next, or we can say consecutive of the previous one. So the general term is n multiply n plus 1, where n is, if we put n1 we get this as 2, if we put n2 we get n3, this particular term as 3, if we put this 3 we get this term as 4. So the general term is n multiply n plus 1, which is n square plus n. Now applying the concept of sum, we get sigma of n square plus sigma of n. Sigma stands for the sum of n square. So now the sum of n square, first n natural number, gives us n into n plus 1 upon, multiply by 2n plus 1 upon 6, and sum of n natural number, n into n plus 1 upon 2. So in the place of n square, sigma, I have applied the concept of sum of square of first n natural number, and sigma n, the sum of first n natural number. Now taking the LCM, taking first common n into n plus 1, we have 2n plus 1 upon 6 plus 1 by 2. Simplifying, by taking the LCM, we get 2n plus 1 plus 3, which gives 2n plus 4. Taking 2 common and then eliminating with 6, we get n into n plus 1 upon, multiply by n plus 2 upon 3. So we need to make a general term in the exercise 9.4, and then we have to apply the concept of sum of n terms of special series. So please see very carefully. Now in this question we have a problem. Question number 4, 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus up to n terms. Now this can be written as an is equal to 1 upon n into n plus 1, because if this is n plus 1. Now this can be simplified as 1 upon n minus of 1 upon n plus 1. If you solve this, you get the same expression, 1 upon n into n plus 1. Now this is the general term I got. If I substitute n as 1, I got 1 minus 1 upon 2. If I substitute 2, I got 1 upon 2 minus 1 upon 3, and so on till 1 upon n minus 1 upon n plus 1. So adding all the terms as the sum, Sn is equal to 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 up to 1 upon n minus 1 upon n plus 1. So all the terms are eliminated except the first one and the last one, which is 1 minus 1 upon n plus 1. So simplifying it, taking the LCM, I got Sn is equal to n upon n plus 1. So I hope you understand this question. In this question, it is a reciprocal question. It is the question having the denominator with the terms. So in this, we have to apply the concept of partial fraction. Please see it carefully. I hope all of you understand all the questions that we did today. So try completing the exercise 9.3, and if you have any doubt, you can directly contact me. So best of luck for the questions. So please try it. Thank you.